Okay, and here we are with the second half of part 3 of the VIS course. This is about the cutting and clipping functions, and in order to use them right, we also have to talk about implicit functions. So they will be used in the cutting and clipping to define where exactly we want to cut, or what slice what slice we want to cut, or where exactly we want to clip the volume in half. What is an implicit function? An implicit function is a function that looks like this, like actually all functions look. Y is fx. F is a function of an argument x, and when we calculate the function we get a result y, and for every x there is exactly one y. If we do the sine of x, or the cosine, or the square, we get one single result. For every x there is one y. We can also make functions that have 2 or 3 arguments. This is about points in a two-dimensional picture, and especially this one is interesting for us because these are the coordinates of a voxel. In VTK we can use VTK implicit function to define such a function. There are a number of them predefined. We can also define our own. For example, one of the predefined functions is this one, where we have x, y and z, and we have a certain constant r, and then the function is defined as x squared plus y squared plus z squared minus r squared. If you remember a little bit of your mathematics, I'm sure you have seen it in the past, this looks like the definition of a sphere with radius r. It's not exactly like that, because the definition of a sphere with radius r would be x squared plus y squared plus z squared is equal to r squared. But here it says minus r squared. But how can we make a sphere out of this? Well, we can say all the points where f, x, y, z is 0, they are on a sphere, because if f, x, y, z is 0, that means that x squared plus y squared plus z squared minus r squared is 0, and it's the same as x squared plus y squared plus z squared is r squared. So this it does define a sphere if we say, well, we are interested in all the points where this function is 0. Then we have a sphere. We can also say, I want to see all the points where this function is 1. It's also a sphere which is a little bit bigger. Or we are interested in all the points where this function is minus 1. That's a little bit smaller sphere. So this function, it is a function. For every point in 3D space, it will give us a value. But if we say we want to see all the points that have value 0, for example, then we have a sphere. The function itself is not a sphere, but all the points that have one specific function value, 0 or 1 or 10 or minus 1, they are in the form of a shape, of a sphere. There are similar functions that relate to cones or cylinders or planes. Well, why do we use them? We use them for separation. So we can say, well, if we look again at this function here, we can say, well, everywhere where this function is 0, that is a sphere. So all these points here on the outside of the sphere, they actually have function value 0. And then the radius is r. And then we have a sphere where this function has value 0. Everywhere outside of the sphere, the function is bigger than 0. Everywhere inside the sphere, the function is smaller than 0. So we can separate the whole world, the whole volume, into two regions. The region where f is smaller than 0, that's actually inside the sphere, and the region where f is bigger than 0, that's outside of the sphere. We can use this for cutting and clipping, because what we can do is we can say we want to see only the values on the sphere. That would be cutting. Or we can say we only want to see, if this is a whole volume here, we only want to see this part of it, only the sphere itself and not the whole volume. That would be clipping. We'll go into that later. Well, let's skip this for the moment. What we can do is, if we have a number of implicit functions, we can combine them. And that is a lot like a set theory. We can take the union of two implicit functions, or the intersection, or the difference. So for example, imagine that you have 3 implicit functions that define this sphere, or yeah, let's say it's a sphere, this one and this capsule. Then we can say I want to have the union of all 3. That would be this object, everything combined. You can say I want to have the intersection. I want to have these areas where 2 of these shapes intersect. So that would be this part here and this part here. Or you can say I want to have the difference. I want to have the capsule minus the spheres. Then the result would look like this. So these implicit functions, each of them defines a certain object, like a sphere or a capsule, and then we can use these operations. So they are called Boolean operations, because you make a union or an intersection or a difference. And by doing that we can create, for example, this ice cream, because how is this ice cream made using implicit functions? Well, we have one implicit function that represents the ball of ice itself. We have a smaller implicit function that represents a sphere here, and then we took the difference of these two. It's actually the big ball or sphere minus the smaller one. So like here we have the whole capsule, but we cut out actually the 2 spheres. Same happens here. And we also have this part here, the cookie, which is basically a cone. But a cone is infinite. A cone goes on forever in that direction. So this line goes on forever, and that line goes on forever. So we cut it. Well, actually we clip it. We say I want to see the cone no further than to here, and there's also a small part clipped over here. So the cone itself is defined by a VTK cone. That's an implicit function. It has an angle of 20, so the angle between these 2 lines is 20 degrees. We have 2 planes, a vertical plane here and here, and that is where we clip the cone. This picture probably shows it better. If this is the whole cone, as I said, the cone itself is infinite, so it will go on forever in that direction. But we define 2 planes here and here to clip it. So this part is clipped, and that part is clipped with the difference function. Sorry, with the intersection function. We intersect this plane here. It separates the world into 2 halves, this, and we intersect the cone with this part, this half of the world. And same here, this plane divides the world in 2 halves, this part and that part, and we intersect the cone with this part of the world. And that's the intersection function that we use over here, set operation type to intersection. Then the ice cream itself, it's a big sphere, the bite is a small sphere, and here we take the difference, the big sphere minus the small sphere. So then we get a function which is called the cream, and for the cone we get a function that's called the cone. So the infinite cone is this one, but this is the clipped cone. And the complete sphere is this one, the green, that's the sphere, the big sphere minus the small sphere. And then we use that cone in this sample function. Remember, the cone is still an implicit function. It's a function, it does not define points or whatever, it's a function. And we have to say we are interested in all the points where this function has a certain value. And that's what we are trying to do here. First we have the sample function, which calculates the value for that function in the number of different points. We cannot calculate the function everywhere, that would be way too many points, would be infinite number of points. So we calculate the value of the function in a limited number of points. That's what the sample function does, in between these bounds. And we take so many samples for x and y and z direction. And then these samples are used in this contour filter, where we say, well, now I'm interested in all the points where this function has value 0. And this is actually the isosurface that we calculate here. We calculate a volume here, we take samples of that implicit function, the cone, and we calculate the values that that function has in a lot of different points. So actually we are generating a volume here, and then inside that volume we are looking for a certain contour, all the points that have value 0. And that is the surface of the cone, which is then sent to a mapper and actor and so on. And similar for the cream. The cream also, the cream itself is an implicit function. It's not an object or anything, it's just a function that gives us, for every point in 3D space, it defines a value. For that one also, first we sample that value in a lot of different points in space. We calculate what the value of that function is, and which is a small volume on its own. And then there we calculate the contour filter. We use the contour filter to calculate an isosurface, and that will be the cone. Okay, this is just a fun example to make an ice cream like that. That's not really what we use it for. We use it for cutting and clipping. So cutting means that we define some kind of surface with an implicit function, and then we cut out exactly that surface out of the volume. So if this is the whole volume, imagine that this is a 3D volume, then this is a plane or another surface, and we take out only that plane out of the surface, so all the out of the volume, so all the other voxels are gone. And clipping, on the other hand, means that if we have a certain volume and we have such a surface defined by an implicit function, we cut the volume in 2 parts and we remove one of the parts. That's clipping. So then we have only this one left. Okay. So for cutting, here's an example of what it could look like. So we have a whole volume and we cut out only this part, the colored part, which is a plane, or we could also cut out this more curved part, depending on what kind of implicit function we use. And then, yeah, of course there's a difference between cutting and contouring. With a contour you would also see some kind of surface inside the volume, like we saw with the knee in the previous part. If you take the isosurface of a knee volume, then you can show the bones or whatever. But what we do here is that our cut is not defined by the values in the volume, but the shape of the cut is defined by an implicit function. That's the difference. Okay, well, I will skip this 2D example. You can have a look at the code by yourself if you're interested. We are mainly applying it to 3D. So, for example, you could have this model, this volume, which is a frog. Actually, in this case, we only have the surface of the frog, so it's not a complete 3D volume, but it's only the skin of the frog that we have here. And with a cutter, a VTK cutter, you could cut out one or more slices out of this volume. The structure is shown here. Here's the VTK cutter. What we add in this case is that since the cuts will now be lines, and the frog itself, as I said, is not a complete volume, but we only have the skin of the frog here. So if we make cuts, then what we have left are lines, the lines that you see here. And to make these lines better visible, we add a small tube around them. That's what this VTK tube filter does. The lines themselves would be very small and narrow, we could hardly see them. This VTK tube filter will make them a bit bigger so we can see them better. That's what's added here. Example of the code. I will not go into details, you can study this also by yourself. But we have a reader that reads the skin. We have an actor that shows the complete object. So this actor here shows the complete frog, the red part. Then we define an implicit function, VTK plane. Remember, this is not an object, this is a function that gives a value for every point in 3D. We can calculate the value using this implicit function. It has an origin, it represents a plane, so a plane is defined by a point somewhere and a normal, so that's what we are setting here. And then we make our cutter, which makes a cut of this volume, the skin of the frog, which uses this VTK plane, which is an implicit function, as the cut function. So that defines where we cut. And then in this case we don't want to make one single cut. You can see here there are a lot of cuts made, but we have 10 cuts which are in a range from 0 to -200. So this implicit function, VTK plane, we take all the surfaces in the volume where this function VTK plane has a value 0, that's the first one. And then since we make 10 cuts in a range from -200 to 0, the next one will probably be -20, and then -40, -60, and so on. So first we take the surface of all the points where this VTK plane function has value 0. Then we take the surface of all the points where this VTK plane function has value -20, and then -40, and so on. So in that way we get a number of different planes. And apparently we have to choose the values in such a way to have nice cuts through the volume. I don't know exactly why it has to be -200 here, not +200, but it has to do with the volume itself. If you would choose a range from 0 to 200, then probably the cuts would be too high, they would be here, and then you don't see anything. But this here, this VTK cutter function, it uses the A-plane, which is an implicit function, and then it, in this case, it generates 10 surfaces in the range from -200 to 0. So for 10 different values, it checks all the points where that function has that value. Okay, and then we do some other things, so we add this tube filter and so on to clearly show those lines. Okay, then the clipping, which is different from cutting, because we cut volume in 2 parts and then show only 1 part. This is again a 2D example, which I will skip. Here is a 3D example of a cow, which we cut in 2 parts. So and 1 part we clip away, we throw away, and the other part is shown. So now we can see inside the cow. And we don't take a slice out of the cow as for cutting. We can now look inside the back part of the cow, which turns out to be empty in this case, like the frog, but we can do the same as a full volume. Similar, we have an implicit function, VTK plane, which by the way could be any other function. We can also define the clipping area as a sphere instead of plane, and the same for cutting. We could have used the VTK sphere instead of VTK plane there. But again, here we use a plane. We do some settings to define the normal and the origin. So with this normal we get a bit of the tilted plane. Then we have the clip function, VTK clip polydata, like a VTK cutter before. We now have VTK, not clipper, but clip polydata, where we say, well, the volume we want to clip is this one, the clip function is our plane function. We do some settings here. I'm sure you can figure out by yourself what they mean. And then we have a mapper and an actor and so on. By the way, what I must say is that when you start doing the exercises by yourself, the coding, you will see that in the newer versions of VTK, in a lot of situations where here we have used set input, you will have to use another method, set input connection. And often where in the example code here we use get output, you will have to use get output port. There are some that is done in newer versions of VTK for specific reasons. So it could be that if you copy paste this code and also for the cutter, that it doesn't work immediately, but you have to do some adaptations, because this code is already from a few years ago and things change, of course. Also a library like this, it evolves over the years. But I'm sure you will be able to figure out those details, and Google can always help. Okay, well, that was this part. Thank you for your attention.